Now, we want to go back to looking at covalent bonds and covalent compounds. And, you know, we had some that we were looking at last time. I'll see if we can't get them up here on the screen. We've got the hydrogen molecule, and remember hydrogen is one of the infamous gang of 7 that exists as an element, not as individual atoms, but as a 2-atom or diatomic molecules. What were the other 6 of the gang of 7? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Well, that's one of them, but I like them in that order, all right? Because that's kind of how they lay in the periodic table, all right? So that makes it easy to remember. Hydrogen, remember, had a single covalent bond between the 2 hydrogen atoms. How did we define a single covalent bond? What is it?
Shared pair of valence.
Shared pair of valence electrons. And if it's a regular covalent bond, as it is in the case of the hydrogen, where do the electrons come from?
The other.
Well, which atoms? 1 from each, right? 1 from each. And they share them out, and that sharing them out is what actually cements, if you will, or bonds the 2 atoms together. Now, that one only had to gain another electron to fill out its valence shell, because what is the maximum number you can put in the first shell? 2. And that first shell is the valence shell for hydrogen. Now, if we skip over to group 7, group 7A, those have 7 valence electrons, all right? So they need to gain 1 more, right, to fill it out with 8. And if you put 2 fluorine atoms together, how many pairs are they going to share? 1 pair, right? That's all they have to share. And that gives each one of them 8. So that's also a single covalent bond between the 2 fluorine atoms, all right? And if we continue on down in that group, you know, chlorine, bromine, iodine, same deal. They get put together with a single covalent bond. And it's a regular covalent bond because each atom contributes 1 electron each to form the bonding pair. Now, if we move over to oxygen, you notice that we had to kick it up a notch. And for an oxygen molecule, we have a double covalent bond, which means what? They share 2 pairs, right? Because how many valence electrons does oxygen have?
6.
6, all right, and it needs 8. But each one of those luckily has 2 that are not paired up, so they pair up nicely, and that completes the octet, or the 8 valence electrons. All right, now, what if we go to nitrogen? How many pairs did we have to share there? 3. So that would constitute then what we could call a triple covalent bond sharing 3 pairs of valence electrons. All right? There you go. That way, nitrogen, which has only 5 valence electrons for each atom, ends up with 8 by sharing out the 3 pairs between the 2 atoms. Now, if we go to something else, and let's just write a little something up here like this. There we have hydrogen chloride, all right, and that is also just a single covalent bond between the hydrogen and the chlorine. Well, by doing that, the hydrogen is going to end up with 2 valence electrons, and the chlorine will now end up with 8, which keeps it happy, all right? And then if we go to water, well, we end up with that kind of a situation, remember, where the oxygen is a central atom, the hydrogens go on it. You know, when you're putting these together, hydrogen's not going to be the central atom because it can only form 1 bond. That's all. But, you know, and then aside from that, it's typically whatever element's present in the lower number is what goes in the middle. All right? And then over here we have another one, also with 3 atoms. This is carbon dioxide. And let's just take a look at the naming convention here. All right, because we'll say a little more about this as we go. The first element is named as an element. All right, carbon. That's the element. The second element is going to be named as an anion. It's not an anion because they're sharing valence electrons here, but we're going to use the anion name. But what is the name of the monoatomic anion derived from oxygen? Oxide. And here, we need a numeric prefix to tell us how many oxygens are there. Now, another trick, too, I don't know why I call it a trick, but anyway. You know, we've got a 1-to-2 ratio here, but with covalent compounds, it's not always of the lowest integer ratio between these things, as we'll see, particularly when we get to organic compounds. Unlike ionic compounds, the ratio between the elements and the covalent compound are not necessarily the lowest numeric integer ratio that you have. Now, what about this one? That is another compound. All right, so it would be called, now there's only one oxygen, and this time, though, we do need the numeric prefix to tell us how many. The only time you would use a numeric prefix for the element in the first position is if there's more than one. If there's only one, just give us a name. But the second one, well, it always has a numeric prefix to tell you how many. Fortunately, this one goes by its common name, water. But if we gave it the systematic name, what would it be? Dihydrogen monoxide, yes. Well, we don't call it dihydrogen monoxide, we just call it water. That's one we use the common name for. Now, isn't that simple? Isn't it? Yes.
For the second one, do you always have to have the numeric prefix?
Yes, the second one always has a numeric prefix. Okay? All right. Well, let's move on to a little something else. And I think for this, we want, let's see what we've got here. We're going to put my little remote. There we go. All right, so to kick it up a notch, the next item on the agenda, or wrinkle on the prune, is determining the shapes of molecules. And for this, we have some rules that we can use that are very simple, and it's just a matter of keeping them in mind. All right. Now, if it is a 2-atom molecule, and it really doesn't matter whether it's 2 atoms of the same element or 2 different atoms of 2 different elements, the shape is going to be linear. All right? So if we look at the first case, which is the hydrogen molecule, well, here would be like a model of that. All right? So each of the balls would represent a hydrogen, and of course the valence shell is highlighted here by the shape. And the nuclei would be right in here. They're lined up in a same plane, straight line. There you go. All right, so that would be the linear shape of a 2-atom molecule where both atoms are the same element. Here is one for 2 different elements. All right? One atom of each different, the 2 different elements. All right, so we might say the hydrogen's the white one and the chlorine is the brown one. All right, because it's a little bigger. There we go. Watch the shape, linear. Take home message, if it's a 2-atom molecule, watch the shape, linear. All right? Because the nuclei are in the same plane, they're in a straight line, if you will. That's where it comes from. All right, now that's pretty simple, is it not? Well, let's kick it up a notch. What if we have a 3-atom molecule? Well, now here it can be a little bit different. Here we can end up with 2 possibilities, and it all depends on that central atom and what's there. It's bent or nonlinear if there's one or more unshared pairs of electrons on the central atom. All right, one or more unshared pairs of electrons on the central atom. All right? Now, incidentally, these slides are in a slightly different order from the one on the web, although I think I changed that. I think I did. I like this order better, so I changed it around. Anyway, what's a good example? Water. All right, let's just digress for a sec and see, oops, that's the wrong one, what we're talking about here. Let's just draw out the electron dot formula for a water molecule. All right. Now, what if we're thinking about water? Here's the molecular formula. What is going to be the central atom? Oxygen, right. You know, there's only one of them, and remember, hydrogen never is going to be the central atom. All right? So let's put it down. Now, how many valence electrons does an oxygen atom have? 6. 1, 2, 3, 4, 5, 6. Now, where can I stick a hydrogen? So the hydrogen will end up with just 2 valence electrons and fill out its valence shell. Well, I think I can put one there, right? And I think I can stick another one there. Now, it's inventory time. How many electrons with that oxygen? How many with that hydrogen? How many with that hydrogen? Well, I think everybody's happy, don't you think? All right, now, what have we got here? Well, between the hydrogen and the oxygen, we have shared pairs of electrons. All right? Those are shared between the hydrogen and the oxygen. Up here, there, and there, we have 2 unshared pairs of valence electrons. All right. What is the relative charge on an electron? What is it? Huh? -1. All right, all electrons have a relative charge of -1. They're all negatively charged. What about particles that have the same charge? Do they tend to attract or repel each other? They repel, don't they? Aha! So these electrons that are associated with this oxygen, whether they're forming a bond or they're not, are trying to repel each other and get just as far away from each other as they can get. But there's a catch. They're all associated with oxygen, so that limits how far they can go. Right? All right, now, when you do that, and when you have them getting as far away from each other as they can get, here is the kind of situation you're going to end up with. You're going to end up with what we could call a bent or nonlinear molecule. Here's the oxygen, here are the 2 hydrogens. All right, between the hydrogen and the oxygen, there'd be a shared pair of valence electrons here and here. What's out here? 2 unshared pairs of electrons. All these electrons on this oxygen are repelling each other. The unshared ones and the bonding ones. And when they move things around so they're as far away as they can go, they carry the hydrogens along for the ride, and you're going to end up with this bent or nonlinear shape of the molecule. All right? Now that's simple, isn't it? So let's go back to the rule. 3-atom molecule, at least one unshared pair on the central atom gives you what kind of a shape? Bent or nonlinear. And water is a perfect example of that. Okay? Now, even if someone were to draw that molecule like this, and you apply your rule, you're still going to get the correct shape. I mean, that's like putting it up there like that. All right, but we know it's been a nonlinear. Why? 3-atom molecule with what? Unshared pairs on the central atom. That's closer to the shape than this is. Although, if you look at it from this perspective, that's the way it would look. But you know, to determine it's actually a bent or nonlinear shaped molecule. Okay? So the rules help you out. Now, the next wrinkle on the prune. We're still not done with 3-atom molecules. So, let's see if we can get our screen to cooperate a bit. And here we go with the other possibility. No unshared pairs of electrons on the central atom, bless you. It's linear in shape. All right? So if there are no unshared pairs of electrons on the central atom, 3-atom molecule works out to be linear in shape. All right? Well, let's take a look at an example of that. All right? So here's one that's 3 atoms and a linear shape. Let's see here. Yeah, that'll do. All right, I'll hide it from you for now and we'll draw it. All right, everybody ready? Okay. It's one we've already seen. It's good old. And what's the name of that one? Carbon dioxide. All right. What is going to go in the center this time, I wonder? Carbon. There's only one of them. How many valence electrons does a carbon atom have? 4, right. All right, let's just put one to a side. All right, there we go. Now, the oxygens obviously need to go on either side. Let's go with that. How many valence electrons does an oxygen atom have? 6. 1, 2, 3, 4, 5, 6. There. 1, 2, 3, 4, 5, 6 on that one. Now, I'll bet you couldn't guess in a million years where we're going to form shared pairs of electrons. And you can actually move some things around here. All right, those two would go together real nicely, wouldn't they? So let's just redraw them to look like that one and there. All right. And then, what about these two? Well, I think I can pair them up too. So here again, move them to the center to show that they're being shared out. All right, there we go. Now let's take a little bit of an inventory, shall we? All right, so how many electrons now with that oxygen? 8. Well, I think it's happy. But nothing else is. There's only 6 there, and the carbon now only has 4. Well, we need some more. So what else can we pair up? Well, I think those two are likely candidates, don't you? All right, so let's go ahead and pair them up. All right. And then those two, well, put them right down here in the middle. No sense leaving them unpaired. Nice. And now, let's do an inventory. All right. Now we know that oxygen has 8. How many do we have on that carbon? 8. How many do we have on that oxygen? 8. I think everybody's happy. how did we have to go about putting them together? We had to put together double bonds between the carbon and each oxygen. All right, so there are two double bonds here, right? Okay, that was the only way you could hook it together and get it to work out. There isn't any other way. All right? Now, come back and examine the central carbon atom. What kinds of electron pairs are on that central carbon? Bonding pairs only, right? Those are involved in bond formation, so those are bonding pairs. So are these. They're bonding pairs as well. And there are no unshared pairs of electrons on this central atom. So what is the shape? It's linear. Voila! All right, here in the center would be the carbon, and here on each end an oxygen. There are no unshared pairs this time to do any repelling. But what about the bonding pairs? Well, they're hooking the carbon with each oxygen. They're trying to get as far away from each other as they can get. How far away from each other can they get and still stay with the carbon? 180 degrees apart. That gives it a linear shape. All three nuclei line up in a row. All right? There you go. Yes?
Are bonding pairs the same thing as shared pairs?
No. Bonding pairs are the shared pairs. Those are the ones that are actually shared between the two atoms. Okay? Unshared are just that. They're not shared with anything else.
Bonding pairs.
All right. These are bonding pairs because they're shared between carbon and oxygen, same here.
Okay.
These are unshared. They're not shared with hydrogen. They're just with the oxygen alone. All right. These are bonding pairs. They're shared between oxygen and hydrogen. These are unshared. They're not shared with anything. The oxygen has them all to itself. But they all repel each other because they all have a relative charge of -1 each. And negative charged particles tend to repel each other. Well, positive charged particles do too, but that's not the issue this time. Okay? Now that's simple, isn't it? Yes, ma'am.
Is this stuff only done with covalent bonds?
Yes. Yes, this would only apply with covalent bonds. Now, where else can it apply? With polyatomic ions, obviously, because they have covalent bonds within them. But we're not getting into that right now. Okay? All right. Simple covalent compounds. All right, back we go. 2 atom molecules, what's the shape? Linear. 3 atom molecules. No unshared pairs on the central atom, what's the shape? Linear. If there's an unshared pair on the central atom, what's the shape? Bent or nonlinear. Okay? Just got to know it, that's all. It's pretty simple. So if I draw out a molecule for you, you ought to be able to tell me the shape, shouldn't you? Yes. Remember your rules. And you will, won't you?
If it was in question form, how would you write out the molecule?
Oh, heavens, I don't know. I might draw out the molecule and ask you to tell me the shape. Or I might ask you to draw the molecule. If it's something simple and I know you can do it, I might do that and then ask you the shape. Oh, there's more. There's another shoe to drop when we get the shapes done. Don't worry. All right. Well, let's kick it up another notch. We're only up to 3 atom molecules, but don't go into heart failure. 5 is as far as we have to go. Okay. Stay down here. All right. Let's go on to 4 atom molecules, and there are 2 possibilities here. All right. Now, 4 atom molecules, 2 different elements. If there are no unshared pairs of electrons on the central atom, all the atoms lie in the same plane. And the shape? Trigonal planar. Trigonal planar. here's what it looks like. All right, we have a central atom. We have the other three bonded onto it. They're all in the same plane. If I lay this down on the desk, every one of those atomic nuclei are in the same plane. They're all at the same level. All right? Trigonal. Well, at least we're not up there close. Trigonal. I'm going to turn the work order on that thing. I'm not going to put up with that much longer. All right, trigonal planar. All right, looks like a triangle, doesn't it? If you connect the dots, all right, like these dark lines here, say that represents the nuclei of each of these three atoms, dotted line running to all those, what are you going to get? Looks like a little triangle, doesn't it? There's where the name comes from. Trigonal planar. They're all in the same plane. All right? Now, let's take a look at something that would give us that. And I'm just going to, go with this. All right, here is something that is not a very common compound. All right, and what would be the name of that compound? Well, what is the first element? It's not one that we've had before, but it's on your periodic table. You don't have to look very far to find it. Boron. All right. So there's only one, so I'm just going to call it boron. Now, what would be the second name for this? Well, the prefix for 3 is tri, T-R-I, so what would it be? Yes. Boron trichloride. Now here's why this one is something you don't see very often. Boron doesn't want 8 valence electrons. It only wants 6. It's a weirdo. All right? It only wants 6. So when you draw it out, now let's see, down here we've got room. All right, when you draw it out, here is how it's going to look. All right, there you go. Each chlorine will have 7. The boron will just have 6. Well, no, each chlorine will have 8 when it's all said and done, and the boron will just have 6. All right. So, if you were to make kind of a dotted line, if we will, between the nuclei of these 3 chlorines, what kind of shape does that suggest? A triangle, doesn't it? And since all 4 nuclei lie in the same plane, they're all at the same level, we would call it a trigonal planar shaped molecule. All right? Now, go back to the rule. 4 atoms, 2 different elements. No unshared pairs on the central atom. What's the central atom this time? Boron. Do you see any unshared electron pairs on it? No. There are 3 bonding pairs. Well, those try to get as far away from each other as they can get because they repel each other like any other electron pairs do. And what are you going to end up with? Well, you're going to end up with this kind of a shape. All right? Trigonal planar. 4-atom molecule, no unshared pairs on the central atom, trigonal planar. You rarely see this because there aren't many elements that act like that boron does. All right? Now, here's something that's far more common, and that is the next one down, which is the trigonal pyramidal. Now, what's the difference? Well, at least 1 unshared pair of electrons on the central atom. 4 atoms, 2 different elements, at least 1 unshared pair of electrons on the central atom, and you end up with what's called trigonal pyramidal. Trigonal pyramidal. All right? Now, what's a good example of that? Ammonia. All right, and remember now, this one, we also use the common name for it. All right, ammonia is the neutral compound, NH3. Ammonium is the polyatomic ion. What's its formula? NH4 with a +1 charge. All right, this is electrically neutral. All right. Now, what's going to go in the middle, I wonder? Nitrogen, right? Kind of wins by default, doesn't it, in this case? All right, there's only one of them, and as we said, hydrogen is never the central atom. Well, you know, that kind of narrows it down. How many valence electrons does a nitrogen atom have? 5, yes. 1, 2, 3, 4, 5. There we go. All right, now, where are we going to stick our hydrogens, I wonder? Now, see how these just solve themselves? Oh, I think we can put one there, and I think we can put one there, and I think we can put one there, and it's done. All right? Because remember, how many valence electrons does it take to fill up the valence shell for hydrogen? 2, and they've each got 2. How many does the nitrogen want? 8. Count, how many has it got now? 8, does it not? All right? Done. But now, what do we note? Here, here, and here. Those are all what we would call bonding pairs of electrons. What do we have up here? Right. We have one unshared pair of electrons on that central nitrogen. Now, what are those things doing? They're repelling each other, aren't they? Here's what we end up with. A trigonal pyramidal shaped molecule. The blue is the nitrogen, the brown are the 3 hydrogens. Now, bonding pairs here and here and here between the hydrogen and the nitrogen. All 3 hydrogens and nitrogen. What's up here? Unshared pair of electrons. Those are repelling these 3 pairs, right? It causes them to bend down. All right? So if I set that on the desk, you notice that the 3 hydrogens are at the same level or plane, but where's the nitrogen? Slightly above it, right? Kind of like a little, here, I'll just set it here, maybe you can see it easier. Kind of like a little pyramid, right? Trigonal, trigonal base, pyramid. There it is. All right? Trigonal pyramidal. There's the shape. All right, so once again, what's the difference between this and this? How do we get from one to the other? Why is this one all in the same plane and this one isn't? Right, this is only shared pairs of electrons on the central atom, no unshared pairs. This one has one unshared pair on the central atom. Both of them are 4-atom molecules. 4-atom molecules. No unshared pairs on the central atom, trigonal planar. One unshared pair at least on the central atom, trigonal pyramidal. There it is. Now that's not hard, is it? No! All right. Well now, one more, and just like the first one, this is a piece of cake. If it is a 5-atom molecule, the shape is tetrahedral. Now, do not go into heart failure over hearing that name. It's very simple. All right. There, we've got it sitting in, ready to go. Tetrahedral. What on earth would be an example of that? Well, here's a very common example for that. The name for this, CH4, is methane. Okay? And in fact, largely what you find in your natural gas pipeline is methane. It's a gas at room temperature. Natural gas is largely methane. All right? And probably in the news a lot because it's one of those greenhouse gases, right? Haven't you heard of it? Yes, heavens, yes. All right. Now, what's going to be the central atom this time, I wonder? Yes, gas is almost boring, isn't it? How many valence electrons does it have? How many does it bring to the party? 4. 1, 2, 3, 4. All right, now, where am I going to stick my hydrogens? Well, I can probably put one there, and I can probably put one there, and one there, and last but not least, there we go. How many valence electrons now does each hydrogen have? 2. How many does it want? 2. How many do we have on the central carbon? 8. How many does it want to fill out its valence shell? 8. Everybody's happy. There it is. Here's the shape that results. A tetrahedral shape. It looks kind of like a pyramid, just a little higher than that trigonal pyramidal, right? Because we've got to add another level there. The black in the center here is the carbon, covered up by these aqua, I guess you could say, 4 hydrogens that are stuck on there. There it is. That's a tetrahedral shape. 3 planes. These 3 are in the same plane. The carbon's a little higher. The final hydrogen goes in a higher plane still. There it is. All right, so if it's a 5-atom molecule, what's the shape? Now, is there anything hard about that? Now, when do you have to look at those pesky unshared or shared pairs of electrons on the central atom? If you're looking at a 3-atom molecule or a 4-atom molecule. If it's a 2-atom molecule, what's the shape? Linear. If it is a tetrahedral molecule, well, there it is. All right? So that's a 5-atom molecule. It's tetrahedral. Simple, isn't it? What do you got to remember? The rules. All right? That's what you got to remember. What to look for. How many atoms first? All right, if there's 2, it's linear. If there's 5, it's tetrahedral. All right, if there's 3 and there's no unshared pairs on the central atom, it's linear. If there's at least 1 unshared pair on the central atom, it's bent, or nonlinear. If it's a 4-atom molecule and there are no unshared pairs on the central atom, it's trigonal planar. If there's at least 1 unshared pair on the central atom, it's trigonal pyramidal. Done. All right, that's all there is to shapes of simple molecules. Right? Yes. Simple. Don't make something complicated out of it. Now, why do we worry about shapes? I always keep saying worry, and we shouldn't be that. We shouldn't worry. It doesn't add anything to our life. But we're concerned. Why are we concerned about them? Because the shape, it goes a long way to explain the properties of these things, particularly when we go looking at solubilities. And that's something we're going to have to consider. Not, however, today, but to get us along the line, there's another wrinkle for our prune, and I will try to bring the screen down for this one, because I don't think I need to draw on the board. And that is the issue of electronegativity. Would someone kindly get my little chair, move it over here so I can tie it down? Because I don't think I need to raise this again today. So, thank you. All right, let's see here. Well, I'm going to hold it. Okay, now this usually works pretty well. I think that'll work. I think that's good. As long as the chair doesn't go flying up, we're in good shape. All right. Electronegativity. Now, what about that? Well, let's define it first. Come on. All right. Electronegativity is simply the attraction for valence shell electrons. The attraction for valence shell electrons. All right. Now, the valence shell, remember, is the one farthest away from the nucleus. All right, and of course, where is it located? Well, for the representative elements, if we note the period, remember, in which the element appears, that tells us where the valence shell is located, right? So if we're thinking in terms of, say, fluorine, where is the valence shell for fluorine? Which shell? Well, which period is fluorine in? 2, right, second shell, all right? That is pretty close to the nucleus. There's going to be a lot of affinity for any electrons that are out in that valence shell, all right? Now, what about chlorine? Let's just slip down and take a look at it. Where is the valence shell for chlorine? Shell 3. It's now a little further out, right? Well, the nucleus there isn't going to have quite as much attraction for those electrons. Now, it still has a lot, but it doesn't have as much as it did with fluorine. This fluorine was closer. All right, what about bromine? Where's it going to be? 4th shell. A little further out yet. What about iodine? 5th, right? Further out yet, right? All right, now, the element with the highest electronegativity on that entire chart is fluorine. All right? Now, what else can we say? Well, the noble gases basically do not have an electronegativity. Why? Their valence shell is full. There's no need to try attracting in or pulling in extras in there. It's already filled up. Forget it. Fluorine's the highest. Now, what happens, I wonder, as you go down that group in which fluorine is found? What happens to the electronegativity as we move down to chlorine? What do we say happened there? Does it get higher or lower? Well, if there's less affinity for the electrons in the valence shell with chlorine than there were with fluorine, it's lower, isn't it? And what do you think is going to happen when you move down to bromine? Lower yet. All right? So, what's the trend? Fluorine's the highest. As you move down the group from fluorine, the electronegativity decreases. Now, what if we go the other direction? All right? Non-metals have the highest electronegativities. Non-metals have the highest electronegativities. Where do you find non-metals on your periodic table? Over on the right. Okay? Metals tend to have the lowest electronegativities. Where do you find the metals? On the left, right? Yes! Guess what happens to electronegativity as you move off toward the left? Increase or decrease? Decrease, exactly. They don't have a lot of valence electrons, they don't have a lot of attraction for them. What do those metals tend to do if they come close to a non-metal that has a much higher electronegativity? Give up their valence electrons, right? What happened to them when they gave up their valence electrons? What happened to the charge? Went from being 0 to being what? Positive, right? If they lost electrons from their valence shell, metals tend to undergo oxidation, remember that little term, and form cations, right? So you can't ever forget these things. They keep coming back and back. All right. Why do the non-metals tend to take them up? Because they've got higher electronegativities and want to attract them right into their valence shell. And which is the one that is the most pull on any wayward valence electrons? Fluorine, right. Because it has the highest electronegativity. Now, knowing the trends, fluorine's the highest. As you move down, it gets lower. As you move to the left, it gets lower. Which element on that friendly neighborhood trusty periodic table would you predict would likely have the lowest electronegativity of anything on there? Where would it be? Where would it be located? Which corner would it be in? Bottom left. Yes. What is the element that's in the bottom left corner in the main body of the table? Francium. Yes. All right. Now that's not hard, is it? Well, is francium a metal or a non-metal? It's a metal. How many valence electrons does it have? 1. Where's it located? What shell is it in? 7. Way out. It's like Pluto. I mean, you know, it's way out there. All right. There's not a lot of attraction for it with the nucleus of the francium atom. So it's easily given up. All right. There we go. Now, fluorine, as we said, is the highest. As you move down, it decreases. As you move left, it decreases as well. All right, and there we go. Now, the next wrinkle, and this is something really for the next time because I can see that you're all getting that blank. I better not sit there. It's not safe. Well, I want to sit somewhere. I'm getting tired of standing. I'm sorry. I'll always move down here. All right. You're saturated, I know, so we'll pick up this next time. Polar versus nonpolar, but I want a little appetizer. All right, now, if I put together 2 hydrogen atoms, how would their electronegativities compare? Would one be higher than the other? Would they be the same? They would be the same. That's right. Now, if they are the same, and they are, if I put together just 2 hydrogen atoms, they each have the same electronegativity, so they each have the same attraction for their shared pair of electrons, right? So, those electrons, those shared electrons, they're probably going to spend as much time with the hydrogen on the left as they are the one on the right, if we look at it that way. Right? Because they each have the same attraction, so they're equally shared out. And the molecule is overall neutral, yes. And there's not one area where there are more electrons than another. So it's nonpolar. There's no partial separation of charge. Now, let's kick it up a notch. Let's suppose we consider the hydrogen chloride or hydrogen monochloride molecule, HCl. 2 different atoms, right? 2 different electronegativities. Which one has the higher electronegativity, hydrogen or chlorine? Chlorine does. Yes, they share a pair of valence electrons, but it's not share and share alike. Who has more pull, more attraction for that shared pair of electrons this time? The chlorine. The electrons may spend just a little more time over on that side than they do with the hydrogen. Now, electrons are negatively charged, right? So if there's more time spent on the chlorine side, that end of the molecule is going to become partially negative, is it not? Now, the overall molecule is still neutral, but the chlorine end is now going to become partially negative with respect to the hydrogen end. And if the chlorine end is becoming slightly negative, what, by extension, is happening to the hydrogen end? It's becoming very slightly positive. We have a partial separation of charge that makes that a polar molecule. All right? A hydrogen molecule is nonpolar. Both atoms are the same electronegativity, same attraction for the shared pair of electrons. HCl, 2 different atoms, chlorine with a higher electronegativity, pulls the bonding pairs closer to it. It becomes slightly negative. Hydrogen end becomes slightly positive. We have a dipole we have a partial separation of charge on the molecule. It's a polar molecule. Now, was there anything really difficult about that concept? No. So on Thursday, then, we're going to pick up with that thread, and we're going to look at bonds and see whether they're polar or nonpolar. And then we're going to come back and we're going to dredge up again those molecular shapes, and we're going to see whether they reinforce each other, the dipoles that is, or do they cancel out? And we'll have fun with that, especially if I can find my meter sticks to bring with me. Alright? Now, don't look so glum. I had fun. Did you? Yes, yes. Well, you're most welcome.